In the last video, we showed how we got the projectile motion equations, and these are the projectile motion equations. The first three are for the y direction, and the last one is for the x direction. There's usually another one sometimes given. It's a range equation, which is a combination, but you only really need are these four to solve anything. And we did say that what's happening is an object goes up. It basically is composed of, it really has an upward part of its motion, and in this case it's moving up and to the right. Well, the Vx is the motion to the right, and the V initial y is the motion to the left. And as it goes up, the y part gets smaller and smaller until it vanishes there, and then on the way back down it starts to get larger and larger until it returns to where it was if it comes down to the same level. So the Vy part changes, and there it's zero. The Vx part, it only has one equation. There we ignore air resistance, so there's no accelerations or decelerations. And so basically in the Vx part, it just moves at a constant speed, which is why we have a very simple equation there. So these are the four equations, and the very general way to solve any type of problem in this is to use these four equations. And then you have to identify the angle, okay, theta, angle. You have to identify the initial velocity and then break that into Viy and Vx. You need to identify time, gravity, we need to identify delta x, delta y, and at some point we could even find the final velocity in the y direction and the final actual velocity, which would be that velocity going down there by simple trig. So these are the things we need to identify, and we need some of these to solve the problem, not all of them. As it worked for kinematics, any three should be able to give us the result. Now this one we're going to know pretty much ahead of time. That's going to be a positive 9.8 because the equations have the built-in minus sign. Depends on what else we're given. In some cases we might be given delta x, in some cases delta y, in some cases t, in some cases the angle, in some cases the initial velocity. And so we'll look at the angle and the initial velocity information first. So there are a number of problems that we can look at. Usually the problems break down into these three. You have an object that lands at the same level. In this case, we don't know what the maximum height is, although we could calculate it, but we do know that delta y equals 0 from the beginning to the end. Delta y is 0. That's one type. Another type is where you start high up and you go to a lower level. Okay? So in this case, the change in y from beginning to end is going to be negative. It's just dropping down. Remember, delta y equals y final minus y initial. So if the final is less than the initial, you have a negative value. The converse of that would be firing up onto a castle, let's say. You fire up like that, and that would be, that change in y would be then positive change from there to there, the change from the final to the initial. That's all important to realize, especially considering they don't always give you the data. They might say delta y, they might give you this case here, and they might say, well, delta y is 28. Well, you have to know that it's going downward, and you have to make it minus. And then the third type, this is I would call this 1 and maybe 2, A and B. And the third type would be where the object is moving along horizontally, okay? And then it comes to a ledge, and then it goes back off, and then it goes down off that ledge. This would be the case where the angle equaled 0 degrees, which is telling, and it will give us some information, and we'll look at that case, if not in this video, in the next one. This case also is equivalent to a lot of the times you get a problem like this where you have an airplane, and the airplane's going along and it drops a package, and of course the package drops down like this, moving forward at the same speed as the airplane, because there is no air resistance. But in the meantime, it is falling. So where does it land? How far from its original point does it land? That would be a typical question. All right, so let's look at a very general case. Probably look at something along these lines, because that's the more difficult one. And so we'll take a look at that. So let's see what we have. So let's say a projectile is launched at, let's say, 60 meters per second at 40 degrees. And we'll say that it is launched from a point 25 meters above the surrounding area. So it's going to drop down. Find delta x. Find the distance. They may say find the range. They may say anything like that. So how do we approach this problem? Okay. We have our four equations. In fact, let me scroll back up here. And let's just drag them down a bit so we can see them a little more. And first thing we're told is that it's launched at 60 meters per second. So we have to identify, as I said, we have to identify a bunch of things. We have to identify the angle, the v initial, which we then have to break. So that angle is 40 degrees. V initial, which is 60 meters per second, which we now have to break into v initial y and vx. We need the time, which we don't have. We need g, which we do have, positive 9.8. Delta x we don't know, and delta y we kind of do know, because we know it's 25 meters above the surrounding area. So if it's launched, it's going to go this way. And so delta y is going to be a minus 25 meters. And so looking at that, if we want delta x equals vxt. All right? So we're going to be able to find vx, okay, because we're going to use some trig. What else do we need to know? We also need to know the time. We don't know that time. So we got to use one of these equations to find the time. So let's see how we do that. First, let's figure out our triangle here. So we have this. This is 60. V initial y is the vertical component. Vx is the horizontal, and the angle is 40 degrees. So the sine of 40 is the opposite over the hypotenuse. So sine 40 degrees equals the opposite over the hypotenuse, which is 60. So v initial y equals, multiply both sides by 60, you get 60 sine 40. You must be sure you're in degrees when you solve this. And v initial y equals, let's see what that is, 60 sine 40 is 38.6 meters per second. So it's as if you threw this thing straight up with a speed of 38.6. As if instead of throwing it at an angle, you threw it straight up at 38.6, and you could then calculate how high it was. So now we know that this is 38.6. So we do know a little bit more about those equations. The cosine, let's do this, cosine of 40 degrees equals the adjacent over the hypotenuse. And so we multiply both sides by 60. 60 cosine 40 equals Vx. And so Vx equals, and let's try that out, 60 cosine 40 is, well, I'm going to round it off to 46 meters per second. It's 45.96. 46 meters per second. So we know this is 46. So we do have quite a bit of information now. We can't solve for this until we know the time, because we do have Vx now. We do have Vx, but we do need to know the time. And the easiest way to find the time is to use which equation up there? To use this equation right here. This one we don't know v final y. We don't know, and it's not symmetric. So, we need to then find what we are going to do with that equation. And let me just extend this page once more. And so we now have delta y equals v initial y t minus 1/2 gt squared. So from before, we could see that we have v initial y, we have g, and we have delta y. Those are three variables in this equation. We have the initial y, g, and delta y. So let's check that out. This becomes a minus 25. This is, let me go back there and look, 38.6, 38.6 t minus 1/2, 9.8. 9.8 is positive, t squared. So we're going to get a quadratic out of this problem here. So we get minus 25 equals 38.6 t minus 4.9 t squared. To solve a quadratic, get 0 on one side. 0 equals 25. It goes over as a positive 25 plus 38.6 minus 4.9 t squared. And so we can solve this. Oops, there's a t there. Critical. We can solve this using the quadratic equation, the quadratic formula, or you can graph it and find out where the parabola crosses the 2 points at which it crosses the lines. Usually one will be positive and one negative, unlike what I've drawn here. Redraw that. And so you reject the negative one. There's the positive one. You reject the negative one because in math it's fine, but in physics you can't have negative time. So if you graph it, or if you solve it using the quadratic formula, you find out that the time, you have two solutions for the time. One is a minus 0.6 seconds, which of course we reject, and the other solution, T1 and T2, is 8.48 seconds, which we then accept. And in fact, finally, now that we know that, we can then now solve for delta x dx t, which now is, let's see what delta x was. Delta x was 46. So we'll scroll back down. We get 46 times 8.48. And so 46 times 8.48 gives me 390 meters. And that's how we do that type of problem. The other ones are very similar. If delta y is 0, okay, that's this type of problem. Okay, it works out very nicely like that. You just put a 0 in there instead of a minus 25. The other solution I'll talk a little bit more about in another video since we're running out of time.